Why am I making them videos when right now podcasts are huge? Right now, live is something that I really love to do, and I think it's a better way to actually deliver this content and this format. So, this is Wild Eco-Evo. Still trying to figure out, not sure if that's going to be the name. That's just one of the names that ChatGPT helped me figure out. But this show is going to eventually have guests. It's going to eventually have a better production. But we are going to talk about the newest news in wildlife conservation, ecology, evolution, all of this stuff that is related to wildlife in some way. Maybe solid molecular, but those guys are kind of weird, so we're not going to really talk about them too much. Starting off strong by getting people divided, which is where we will start today, because I was planning out a video. Usually what I do is I go to science news. I go to Google News. I go to some type of science area. And I just look, hey, what was just published? What are some recent things? Maybe I'll go to a new paper. Maybe I'll go to somewhere else. I am also waking up. The only guest that we have today is my coffee and possibly my cat if he stops being a pig. Anyways, this is the paper that I found. I guess this is the news article talking about the paper. And it got me interested because it says a hidden line deep in the ocean divides animals into two camps. I was like, well, what's going on here? What do they mean by a hidden line? A lot of times pop sci articles are just kind of bullshit, so I didn't even know what they were talking about. But as I went through it, I found this is actually really, really fascinating. So we know that organisms live deep underground, deep underwater. Organisms can live very, very deep underwater, thousands and thousands and thousands of meters below the Earth's, below sea level. For some reason I keep thinking they're underground, and that's not true. It's just a different underword. Thankfully, they're not living underwear. Haha, I need a laugh track on here. I can get laugh tracks on here. So, what they found is that below a depth of around 4,400 meters, that is about 14,500 feet in freedom units, most of the creatures lurking in the darkness have soft, squishy bodies. And only above that line do hard-shelled mollusks exist. So let me break this down into not text. Let's open up the whiteboard. Look at how prepared I am. I even had the app open. I should have opened it because now we're just sitting here awkwardly. If you're in the chat, let me know where you're in from. This is a live show. I want it to be live. I want to interact with you. So imagine watching your daily Good Morning America news, or good morning wherever you're at. If you're from India, good morning India, or I guess good evening, good night, hello. We can interact. Imagine watching Good Morning America and saying, hey Pat, like that tie. Cool. So what this paper is saying. Okay, if we get the pen going, come on, pen. Let's say right here, boom, look at this. We have sea level, okay? So this is you at the beach, chilling out, having a good time. And I want you to know that at sea level, the Earth's atmosphere is 1 ATM, 1 atmosphere. Okay, we're gonna keep that in mind. But if you go all the way down to, let's say right here, is 4,400 meters. Below this line, squishy. All the organisms are soft-bodied and squishy. So think about things such as there's that stereotypical blobfish, which I should double check if that's actually down there or not. But soft-bodied organisms, so softer corals. You have like jellyfish, you have squids, you have these soft-bodied organisms below this line. And above this line, above around 4,400 meters, that's when you get hard-shelled mollusks. Now, I started ruminating on this, started thinking, and this did not make sense to me at first. Did not make sense at all. Because what happens, the more you go underground, the more you go underwater, the deeper and deeper you go, the more and more pressure exists, okay? In fact, it's surprising, it's very surprising, for every, I believe it's 10 meters, wait. Every 10 meters you go down lower, I had this written down and it's gone now. The atmospheric pressure increases by 1. Okay, so yes, by 1. For every 10 meters where you decrease in depth, or I guess increase in depth because it's a backwards metric, you have a corresponding increase of 1 atmosphere. So think about it in this way. If you are at a depth of 10 meters, you swim down 30 feet, you are having double the pressure as if you were standing on sea level. Okay, so if you're down here, let's say this is 10 meters, we're going to use a log scale here, you would be feeling, your body feels as if it was double. Okay, right now we feel kind of good, we feel nice and good. You may be at sea level. If you're up in higher elevation, you know you feel a little bit lighter. Now imagine feeling double. Now imagine you are at 4,400 meters. You are deep, 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 deep below the surface of the water. You would be feeling 440 atmospheres. To have a better understanding of this, because I looked this up, this study goes down to a depth of about 5,000. So they go to about 5,000 meters. 5,000 meters, not 500. So there, based on that 10 meters to 1 atmosphere rule, we know you get about 500 atmospheres of pressure. Okay, the Earth's atmosphere feels 500 times greater at a depth of 5,000 meters. This is a point where humans cannot exist. You need specialized tools, you need submersibles. This study used entirely footage from remote-controlled like submarines that can withstand these high pressures. Because at a pressure of around 5,000 meters, I do not know the conversion to PSI, but pounds per square inch, I looked this up. This would be the equivalent of having every square inch of your body receiving the weight of a small elephant. Let me repeat that. At a depth of 5,000 meters, every square inch of your body feels like it has its own elephant weighing down on it. That is the pressure we are dealing with. A small elephant, okay? So maybe that actually doesn't work. Every 2 square inches has 1 African elephant. If we go for a small forest Asian elephant, this would be a good one. In fact, let me, you know what? I'm going to look this up, okay? Because it takes 2 seconds. Oh gosh, I'm revealing things. 5 ATM to PSI. So that's 7,347 pounds per square inch at a depth of 5,000 meters. 7,300 pounds on every square inch of your body. That is the pressure we are dealing with down at these depths. So how does that relate back to, well, hard-shelled mollusks? My thought would be that we would actually find more hard-shelled mollusks at deeper depths. Why? Because they have hard shells. They're like a hard submarine that can withstand the pressures. Now, of course, many mollusk species, it's for defense, not for counteracting pressure. But the fact that we have small, soft, squishy organisms at this depth, and that's it. Those are the only organisms they found there. Squishy, soft organisms. So I mentioned the blobfish earlier. There's that classic picture, blobfish. And this is the picture that people see most often. They're like, oh, this is the blobfish. Look at how ugly it is. It looks like a blob. Ha 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 ha. That's not actually what it looks like. It actually looks like this. Okay. It looks like a regular fish. What happens is that when the fish is brought up from the ocean depths, I'm not even sure how deep these areas are, between 2,000 to 4,000 feet. Okay, so these fish are around 2,000 to 4,000 feet, so nowhere even close to what we're dealing with, right? We're dealing with 4,000 meters, so about a third of the depth. At this depth, this is what they are used to. This is what they are adapted for. That's actually a bad argument, whatever. But when they get brought up to the surface, that pressure differential causes their tissues to fundamentally break down, resulting in a blob. Because it's just destroyed them entirely. If you've ever gone diving, imagine the worst type of bends you could possibly imagine. It's why you have to surface slowly if you are diving at greater depths, because it can mess you up. Okay. So then why are there only soft-bodied organisms at these depths? Why are there no hard-shelled organisms? Which, again, my thought process when I was reading this, not being marine biology, being very clear about that, I'm not a marine biologist, I'm a terrestrial biologist, which means I have less job opportunities. There are no hard-bodied organisms at those depths. None at all. Found out, because if you actually read this paper, this is published in Nature, there's a concept called carbonate compensation depth. What does that mean? I had to know, looked it up, read the paper. So when a hard-shelled organism makes their shell, okay, you have a mollusk, you have a let me show you a typical mollusk. Your clams, you have your well, not the snail gastropods, a hard-shelled organism. Yeah, your clams, basically anything that makes seashells up on the beach, right? Any organism that is built like that, they are absorbing calcium carbonate from the water. And then they're using that calcium carbonate to build their shells. Calcium carbonate is just diffused throughout the water, and then the organisms can uptake it, use it to, well, build a shell. Said the exact same thing, just with more words. At those depths, there is no more calcium carbonate diffused into the water. And so the organisms are unable to produce shells. It is a physical resource constraint. There is simply none of the resources needed to make shells at those depths. So think about that. There are organisms living down at the ocean depths, which they actually have pictures of them here. And so, for example, K right here, this is a octopus. Oh, I believe I can open it up. Yes. K is found at a depth of, where is it? 5,000 meters. Okay, so this octopus, squid, what is it? This is a Grimpoteuthis? Dumbo octopus. So there are Dumbo octopi, or octopus. I saw someone mad about this on Threads. Anyways, this is at a depth of 5,000 meters. This is at that depth where the Earth's pressure is the same as having an elephant on every square inch of your body. And it's just vibing down there, looking cute as hell. The Dumbo octopus. They have other adaptations in order to exist at those depths, but they are unable to make a shell. Even if they had the evolutionary potential, they have the structures, they descended from organisms with hard shells, they would be unable to make them at these depths. And what the researchers found, because they sampled many sites, going from a couple thousand meters down to so less than 3,000 meters is probably the highest they went, down to about 6,000 meters is the maximum depth based on this figure. And they found, based on this figure here, there is a transition zone from around 4,300 meters to about 4,800. So there is, if you look at these graphs, basically what they're saying is peaks just tell you where an organism is most abundant. So you see here, if we look at mollusca, this is really cool. Bivalvia, which does have things like your bivalves. So bivalves. oysters, clams, that type of stuff. They are found at depths. Oh gosh, where is it? 44,000 meters. But once they start hitting that transition zone at around 4,300, it starts to trail off. And a lot of them have a dramatic decrease. You look at these graphs, right? Okay, they peak at around 4,300, completely gone by 4,500. For this little peak right here. For this is for Polyplecophora, but for the bivalves, it's about the same. And if you look across all of these, you see how often the peaks dramatically drop at 4,300 meters. This is that area where calcium carbonate is no longer diffused. Through this region, this is when it starts to drop off. And then at depths below 4,500, below 4,800, you have none. And so that is when you only get those soft-bodied organisms. But what was fascinating, I was like, okay, this is a major resource constraint. You know, imagine if you are looking at arboreal birds that need trees, and then you get to an area that says no trees, and it's like, well, we're not going to see any more birds, you know. Like, that's the thought process. They find that there's actually no differences in taxonomic richness. Species diversity is the same in these areas. It's just that they compensate. There are more species down at these lower depths. Because even though there's no calcium carbonate, there are other ways to live and adapt with the pressure of an elephant on every square inch of your body. So I thought this paper was fascinating. It's actually open access, so you can read it without needing to pay money to greedy publishing firms. So I would definitely recommend reading it. It's a very cool paper. It's pretty clear, very straightforward. They just went out, they had little submersible, they got images from submersibles. Yeah, I was like, there's not another word after that. They're just submersibles. But ones that you can like remote control, utilize. And they actually processed all of the images manually. So I believe they had 50,000 images that they went through, and they categorized them as to the best of their ability. Sometimes they could get down to species, sometimes you just get down to the genus, and that's totally fine. I think a few times they had just family level organisms, and they did everything that were animals greater than 10 millimeters. So 1 centimeter, which is insane still. Like, that's such a crazy small cutoff. But they were able to find it. So yeah, I just wanted to share this paper today because I thought it was super, super cool. I also love open access papers. So I think throughout this, I'll try to make sure it's only open access because I want you to be able to read these papers too. But this is Wild Eco-Evo. Still trying to figure out what it's going to be like. Still trying to figure out all the little components. We're about to hear a motorcycle. Just fair warning. But I was also planning on a few other small videos. These shows are only going to be maybe 20-30 minutes long at this point. So sign on. We'll try to do them a few times a week right here in the morning because that's when I work best. But I am developing out a little YouTube short thing, just a short little video on a fascinating organism. The spider-tailed horned viper. Pseudocerastes urarachnoides. So if we look at this picture, so let's open up this image in a new tab. This is not a spider. This isn't a little camel spider. That's its tail. With all these little spindly bits coming off. That is this spider's tail. That is a snake's tail. Apologies. So this is a viper species found in western Iran. So it's endemic there. It was actually only somewhat recently described. First specimen was found in 1968, probably known by local people for much longer. But here we go. Here's actually a cool little range map. I mean, only found in a very small area, at least known. It's likely in other areas, but you know, we just don't have sampling. We don't know the full limits of the species. But what's incredible is what that tail is used for. What that tail do, though? It is actually a lure So if I remember right, um, where is, I believe this is the one. Yeah, so this video is a fantastic representation of what this one does. Also just really good drone footage. This is from Incredible. Like that's the channel name. So just credit where credit's due. But if you look out, you know, they're showing you birds, they're showing you the beautiful areas out here in Iran. But we're going to start seeing the spider. So that's a spider. Those are spiders. The birds there do eat spiders. Many birds do, of course. But right here, this is the viper. So this thing moving around, this is actually the tail of the viper. And you're going to see it. So look, the bird goes up, tries to grab the spider's tail. Boom. The snake just grabs him. Like, we can watch this again. So again, it is a lure. They actually just shake their tail around. I mean, also just a beautiful snake with an incredible adaptation. I thought this was just mind-blowing. Also, I'm not sure, like, if this person actually took all this footage and only has 80 subscribers, that is a damn shame. But you can really see the tail here. I mean, just incredible. So this is a great example of just like incremental adaptations over time. The little components, little scales probably started to expand, probably started to be a little bit more elongated, and eventually they looked a little bit like a spider. Then over time, they expanded a little bit more, expanded a little bit more, expanded a little bit more, until they looked like this tail that we have now. This tail that almost looks like a camel spider or a centipede or something, so just an insect of some type. And they use it to lure in birds. So I actually just did a little bit of a deep dive on rattlesnakes that we have, of course, in the Western Hemisphere. And their rattles are basically these hollow segments that when shook make noise. And generally speaking, with these groups, it is believed that snakes would actually shake their tails before the advent of the rattle. And they would do it as an auditory cue to be left alone. If you've ever walked up on I've seen it with bull snakes or rat snakes before, and they're shaking their tail and they're hitting something. It is loud, it is distracting. Many snakes do have caudal lures. So caudal lures. And all this means is a way of wiggling the tail to attract a prey source. And yeah, you see this actually quite a bit. So like here, for example, is a very young cottonmouth. Their tails are actually quite brightly colored. Bright yellow. I've seen this in cottonmouths. I've seen this in bothrops. I've seen it in fertilances. And it's a really good strategy. It's seen, I believe, a little bit more often. Here's a copperhead that has it as well. Again, little yellowtail. And it's most often used to attract a bird, attract maybe a rodent at most. But I'm feeling fairly certain. I don't know if there's any papers that have actually looked at it specifically with the Pseudocerastes, but it is very likely that this just had a slow evolutionary path from caudal luring just to get birds, maybe had a brightly colored tail, and then some organism had a genetic mutation that made it look more similar to a spider, and they caught more birds. So their genes got passed on. And the next generation looked a little bit more like a spider. So their genes got passed on because they caught even more birds. And then the next generation looked a little bit more like a spider. And my thought process is that they actually do look like camel spiders. I believe that's what it is trying to mimic the best. So if you look at camel spiders, they're also found in that region. Of course, the pictures are stupid. But I mean, you look at this, you look at the caudal lure of a Pseudocerastes. So let me actually just do it here. Boop-a-da-boo, boop-a-da-boo. This is a pain. Like, I can see how they would be mistaken. I could absolutely see that this is the reason. This is what is a type of mimicry almost. I'm not sure how you actually would test that it's this, but it looks so damn similar. And it's probably something along the lines that birds would eat camel spiders. They have a preference for it. Maybe some ancestral bird did. And so the tails that looked a little bit more like a camel spider, well, they, again, passed on their genes, passed on. But yeah, so this is the first episode of Wild Eco-Evo. I know it's not perfect. I know it's not fine-tuned. I know it's not polished, but that's fine. What we're going to be doing on all of these whenever we do them, I'll be very honest, I wanted to just do it today. I would love to tell you when the next one is, but I have a conference like I have to hit up next week, and I just have many things that are pulling my focus at the moment. But we will be doing these often. I believe we'll be trying to do them 2 to 3 times a week at the start. Let's plan for twice a week, and each of the time we're going to break down a paper, share some conservation news, share some news about what's going on in the world of biology, and then just talk about some cool creatures. For this next episode, I will be working on getting a guest on, polishing it up, making some better graphics, maybe changing the name, who knows. But if you liked this, make sure to subscribe, make sure to do all those things that YouTubers tell you to do, and yeah, have a wonderful day. I will be actually promoting this ahead of time too, not 15 minutes before I go live. So yeah, thank you. Have a wonderful day. And yes, I want to make sure I plug this in. Remember to learn adventurously. There we go. We did it.